Hello everyone. Today we'll be presenting our project titled Flush-Based Cache Side Channel Attacks and Defense. In this project, we explore potential attack scenarios where an adversary has access to flush instructions. We also investigate detection techniques and defense mechanisms to mitigate these types of attacks. We start off with introducing the problem and our motivations for this work. Then we delve into background and become familiar with some concepts and works that are necessary for understanding this work. Next, we discuss our threat model, and in the end, we show our methodology and the results we have until now. So, modern computers and powerful, complex computers are vulnerable to a large number of attacks. And even with robust software protections, the underlying hardware can still be attacked. One of the key threats we face today are side channel attacks, and these basically exploit subtle physical effects of computation to leak sensitive data. And what's especially dangerous about them is that they can undermine well-established security protections that we have nowadays. And this isn't just theoretical. On the right, you can see a few recent headlines finding products from Google, Microsoft, and Apple vulnerable. Google, for example, confirmed a cyber espionage campaign using sophisticated malware. Microsoft had to patch a side channel vulnerability that leaked data from Intel CPUs. And even the Apple's M series chips have been exposed to new speculative execution exploits like SLAP and FLOP. So, coming up with mitigations for side channels is very important for the security of our systems. The research community has proposed a wide range of techniques that can be broadly categorized into two groups: non-ML based mitigations and ML-based mitigations. Non-ML-based mitigations typically rely on architectural or programming strategies like cache partitioning and randomization, constant timing programming, or compile-level control flow mitigations. While these can be effective, they often come with significant trade-offs. They are platform dependent, they require a lot of manual effort to implement, and they can introduce considerable performance overhead since the protections will be always on. ML-based mitigations, however, aim to overcome this limitation. The main strategy here is to first detect the presence of an attack and then apply countermeasures. However, for this to work effectively, the ML models must generalize well and be able to detect a broad range of attacks. This requires high-quality training data, which is often difficult to obtain, especially for rare or sophisticated attack techniques. Also, with every detection scheme, attackers might try to evade detection by slightly altering their behavior to fool the detector model. So the model should be able to generalize to unseen attacks as well. But how can we train an ML-based detector that generalizes well to all attacks and overcome the difficulties of gathering training datasets? Past research has shown multi-agent reinforcement learning is an effective tool that can be leveraged for this purpose. Specifically, RL can generate cache side channel attacks that bypass defenses and is deployable in real machine. Also, RL-based detectors have the ability to generalize well to unseen attacks and detect a wide range of attack scenarios without being trained directly on them. However, previous works have not included flush instructions in their threat model. This means they do not cover attacks like flush reload or flush flush. The goal of our project is to extend the previous works in this area and extend their threat model by giving the attacker the ability to flush data from cache. And we also would like to observe if multi-agent reinforcement learning is able to generalize to flush-based attacks and defenses as well or no. Okay, we start with explaining what timing-based side channel attacks are. Before diving into side channel attacks, let's briefly review how caches work and why they matter for performance and security. Modern processors rely on a memory hierarchy to reduce access latency. At the top of this hierarchy, we have the smallest and fastest storage, like CPU registers and L1 cache. And as we move down to L2, L3, and finally main memory and disk, latency increases and speed decreases. The last level cache, usually L3, is especially important because it's shared across all cores, and that shared nature makes it a common target inside channel attacks. Now, a cache hit happens when data is found in the cache, and this basically means that we're going to have a fast access. And a cache miss means that the data has to be fetched from the lower levels like main memory, which is much slower. And the diagram here on the right visualizes this trade-off. As we go down the pyramid, storage gets larger but also slower. So, timing-based side channel attacks basically exploit the variations in the time it takes to access data in a computer's cache memory. The attack can leak cryptographic keys and encryption and decryption algorithms like AES or RSA, and it also can break isolations between sandboxes, applications, and virtual machines. Here we show an example. A flush reload attack is shown to demonstrate how the attacker can learn information from timing variations. We show only one cache set here, but the mechanism applies to all cache sets in the same way. So for this attack to be deployable, the attacker and victim should have some shared memory pages, like shared libraries. The attack has three phases. In the first phase, the attacker flushes the cache completely. And here the blue rectangles show a cache line which has been flushed. So all of the attacker's data will be flushed from the cache. Then in the second phase, the attacker lets the victim program run and access its data. During this time, the victim might access the flushed memory addresses. And in the final step, the attacker accesses its own data and measures the timings. A cache hit indicates that the set has been accessed by the victim data before. So, to understand how this timing difference can be exploited directly, we explore or show some code snippets here. But before that, this diagram here shows a cache component which is shared among two programs. One may be the attacker and one the victim in the case of secret leaking, or in the case of breaking the isolation, one might be the sender and the other the receiver. So on the left side here, there are two code snippets that show how victim secret can be leaked through the shared cache. So in the first snippet, the victim the victim program accesses an array using the secret as an index. This brings a specific cache line into the shared cache based on the secret's value. Later, the attacker can access the same cache lines as those that are shared among the victim and the attacker, and measure how long each access takes, as shown in the flush reload attack. And basically, the cache line that responds fast reveals the index and thus the secret. And in the second code snippet, the code path taken depends on whether the secret is true or false. Even though this doesn't access memory directly based on the secret, it still affects what gets executed and what ends up in the cache. The attacker can then probe the cache to infer whether the branch was taken, and indirectly learning the value of the secret. Now we will discuss reinforcement learning and multi-agent reinforcement learning. So, reinforcement learning is a form of unsupervised machine learning where learning happens through trial and error by interaction with the environment. RL has some important notions that we show here. The agent is the decision maker or the model that we train. The environment is what our agent interacts with and learns from. The state or observation is the agent's current view of the environment, and we can define how large or what parts of the environment we want our agent to be able to see. The action is what the agent decides to do. The reward is a signal that the environment gives to the agent and basically shows how good or how bad the action that the agent has taken was. A step is one interaction between the agent and the environment, and an episode is a full sequence of steps from start to some terminal condition. Here on the right, you can see a typical RL loop. The agent receives a state from the environment, takes an action based on that, gets some reward, and moves to the next state. So by keeping doing this, the agent learns to optimize its actions and maximizes its long-term reward. In multi-agent reinforcement learning, we have multiple agents interact with the environment and maybe each other. And these multiple agents can be working together for the same goal, or they can be trained against each other as competitors. Training competitor agents can lead to better performance for both agents as they will learn from each other and try to overcome each other's. Now we'll discuss the previous works that we have built our project upon. The first work is AutoCAD. So in AutoCAD, reinforcement learning, it's actually a reinforcement learning framework to automate the discovery of cache timing attacks. And as you can see on the right, the environment simulates a cache which the attacker agent interacts with and tries to come up with a sequence of memory accesses that help it infer the secret of the victim in the cache. So basically, by leveraging deep reinforcement learning, it systematically explores microarchitectural vulnerabilities without human-crafted heuristics. In this work, it has been shown that RL can find attacks on a diverse configuration of black box caches. It can find attacks to bypass countermeasures or avoid detection, and it can also even find new attack patterns. So the attacker in AutoCAD is able to do three types of actions. It can access a data in its own address space. It can wait for a victim access, and it can also guess the secret. As for the observations and the data that attacker is able to get from the environment, the agent can only measure the latency of its own memory accesses. As for the rewarding mechanism, to guide the agent, the attacker gets a positive reward when it can correctly guess the secret, and a negative reward when it can't guess it. Also, to encourage the attacker to find the secret in as few steps as possible, at every step it receives a small negative reward. Here, the overall framework of AutoCAD is shown, and as you can see, the RL engine is provided with the attacker and victim configurations and finds some memory access sequences that reveals the secret. And then this memory sequence later will be analyzed and tried on real machine. So the other work is MACTA, which uses the attacker agent in AutoCAD and generates a new detector agent to propose a multi-agent reinforcement learning framework where attacker and defender agents co-evolve and simulate realistic cache timing attack and defense scenarios. In this work, they show that the trained attacker is able to act more stealthily in presence of a detector, and that the trained detector can generalize to unseen attacks. And this is how they formulated the problem. The cache simulator is the environment that the agents interact with. And since the two agents are competitors, they do not share anything with each other. So they basically have their own actions, observations, and rewards. And an important notion here is that for training a good detector, the model should be trained with both attack and benign data to be able to distinguish them and do not detect benign data memory accesses as attacks. So in Makta, the attacker agent is configured as it was shown on AutoCAD. However, the detector agent is a completely new agent that needs to be configured. And we here show how it's configured. So the detector agent should decide to raise an attack flag or not. And its observations from the environment is basically broader than the attacker. And it can see the latency of all memory accesses, as well as the process ID of the process that has made that access. And as for the rewards, there is a set of rewards that encourages detection, and by basically giving positive reward to every attack detected. And also to reduce the false positive rate, a negative reward is given to every false flag raised. So to train the agents, they train them iteratively, each for some number of specific steps. And also they have a pool of checkpoints for each of the agents. And every time when one of the agents wants to be trained, that agent will be trained against a pool of the opponent agents. So this basically ensures that the agents will not forget the behavior of the early checkpoints. For example, as an attacker agent will evolve over training with this pooling methodology, they make sure that the detector agent will never forget the behavior of the first checkpoints of the attacker. And it basically will be able to detect all attacks that the attacker agent came up with during the training. Now we'll discuss our threat model. So in our threat model, we assume that the attacker and victim share a cache, and the attacker and victim should share some address spaces. There is no root privileges for the attacker, and the attacker can measure the timing of its own memory access only. Also, the attacker is able to do flush instructions as well. Now we'll discuss the methodology that we have in incorporating flush instructions into the discussed frameworks and the results we have until now. So we modified the attacker agents to give it the ability to do flush. So now the attacker has an extra action, which is flushing an address from the cache, and the reward and observation will remain the same. So here we show the results of an attacker with flush capability. We have done our experiments with two cache configurations, a two-set two-way cache and a one-set 12-way cache. The first plot shows attacker's correct rate, which basically is the percentage of the correct attacker's guesses. As an attacker, we expect this value to increase over training. And as you can see, this value increases and the attacker is able to reach 100% correct rate in guessing the secret. The second plot shows the length of each attack sequence, and based on our rewarding mechanism, we have encouraged the attacker to find the secrets in as few steps as possible. So we expect this number to go down over training. On a plot, we can see that the attacker trained on one set 12-way cache is able to attack in only 4 steps. And here we show the configurations of the attack scenario. in the 1Z12A cache. So the attacker and victim share the address 0, and the attacker is able to access a wide range of addresses while the victim is given either 0 or no access. So in the attack, the attacker first this is the attack that the attacker agent has come up with. So the attacker first flushes the address 0 from cache and then waits for the victim to make an access. After that, the attacker will access address 0 again and measure the timing. Based on the timing, the attacker will be able to guess the secret.
In this section, I'll walk you through part of our project related to flush traces and benign scenarios, which are essential for training our multi-agent reinforcement learning-based attack detector. Let's start with the big picture. In reinforcement learning-based detection systems, especially for cache-side channel attacks, the detector learns to classify events or behaviors as either benign or malicious. Now, this sounds simple at first, but what the model sees are just memory accesses, timing differences, and instructions like flush. If the detector is trained only on malicious data, it may start treating any unusual behavior, including valid, normal uses of flush, as an attack, which is not good. This is why benign scenarios are essential. They represent programs that perform memory operations, possibly including flushes, but are not attacks. They help the detector learn the difference between malicious behavior that tries to leak secrets and normal system behavior that might look similar at the surface level. In other words, they reduce false positives and improve the robustness and generalization of the detector. Let me give a quick example. Imagine a database system that invalidates cache lines during transaction commits that involves flushing data. If our detector thinks any flush is malicious, it'll raise constant false alarms, making it unusable in a real-world setting. And now, why are we so focused on flush traces? Because many popular cache timing attacks rely heavily on the flush instruction. In these attacks, the attacker flushes a specific memory address from the cache, waits for the victim to access it, and then reloads it to measure the access time. If it's fast, it was cached, meaning that the victim accessed it. If it's slow, they didn't. But here's the catch. Flush is not only used by attackers. Normal programs are also use flush instruction. For example, hash maps use periodic cache invalidation. SGX enclaves use flushes for memory consistency, especially via interfaces like hardcores. Persistent memory systems like Recipe ensure memory durability using flushes, and databases like Silo flush cache lines for correctness in concurrent transactions. So, to train a detector that can correctly identify attacks without flagging every flush as suspicious, we need examples of normal flush uses. And that's why we collect flush traces from benign workloads. Now let's talk about how we actually collect these traces. We use the Gen 5 simulator, which is a cycle-accurate simulation platform widely used in computer architecture research. Specifically, we executed our benchmarks in SE mode. In SE mode, we don't simulate the entire operating system. Instead, we run user-level programs, which is perfect for our goal of tracing application-level flushes and memory behavior. It also makes it easier to control and repeat experiments, and we can avoid unrelated kernel-level noise in the trace. We also use a Gen5's fast-forward option to skip the first 10 million instructions, since that part of the program mostly includes initialization code. This allowed us to jump straight to the meaningful execution phase where actual memory access patterns emerge. To simulate a realistic cache hierarchy, we enabled both L1 and L2 caches, setting the L1 data cache to 64 kilobytes, the L1 instruction cache to 16 kilobytes, and the L2 caches to 128 kilobytes. We also allocated 16 GB of memory in the simulated environment. This setup ensured that we could capture precise memory behavior, including flush instructions, under realistic but controlled conditions using Gen5. But learning benchmarks wasn't plug and play. We had to modify the benchmark programs to better suit trace collection. In particular, we disabled multi-threading and made the benchmarks learn in a single-threaded mode. This helped us isolate memory access patterns and made the trace analysis much simpler and cleaner. We also compiled the binaries using static linking. In that way, we eliminated noise or variability introduced by dynamic or shared libraries. These adjustments made our trace collection much more reliable and accurate. Looking ahead, our future work includes two major tasks. First, we plan to complete the collection of benign flush traces. This includes learning more benchmarks and collecting a diverse set of normal flush behaviors to improve the quality of training data. Second, we will train the attacker detector setting in a multi-agent reinforcement learning framework. This setup allows both attacker and detector agent to learn and adapt together, which helps the detector generalize better to unseen attack strategies. Thank you for listening. Let me know if you have any questions.